In this video, we'd like to look at the zeros of polynomial functions. You might recall that in a previous video, I mentioned that when we found the x-intercepts of a function, they are called sometimes the zeros of the function. So we're just finding the x-intercept, but with a new name. Sometimes they're also called roots or solutions. You may hear that from time to time. One thing that we talk about for one of those roots or solutions is multiplicity. So this is how many times a factor occurs in the factored form of the polynomial function. The multiplicity affects the graph of the function at the zeros as follows. If a factor has an even multiplicity, so 2, 4, 6, or so on, then the graph touches and turns at the zero. If a factor has an odd multiplicity, then the graph crosses the x-axis at said zero. So in these next examples, we would like to determine the zeros of the polynomial function. We need to describe their multiplicity. And then because of their multiplicity, we can tell something about how the function behaves at those zeros, whether it touches and turns around or crosses the x-axis. So let's go ahead and look at the first example here. They want us to find all real zeros of the polynomial function. So this one's already in factored form. This is fantastic. We don't have to do a whole lot of work. There are three factors: negative x, x plus 4, and x minus 1. So this is where the multiplicity comes in. Notice it says factor in factored form. So this is factored form. And you'll notice that this factor right here, x minus 1, is to the second power. That's going to tell us that that's multiplicity 2. All right. So find all the zeros. Well, that just means take the function in factored form and set it equal to 0 and solve for x. So 0 equals minus x times x plus 4 times x minus 1 squared. If I have a bunch of things multiplied together and their result is 0, that means that any of those things could have been 0. Therefore, I just take each factor and set it equal to 0 and solve. Okay. So negative x equals 0, you would multiply by negative 1, you get x equals negative 0, which just means 0. That's one of our zeros or roots. X plus 4 equals 0, you would subtract 4 from both sides, and you would get x equals negative 4. That's another 0. And the last one here, x minus 1 squared, you would take the square root of each side. These would cancel. Technically, remember, you'll get plus and minus over here, but because it's 0, it's just 0. So we have x minus 1 equals 0, or x equals 1. Now, the first two are multiplicity 1. This one is multiplicity 2. And remember, that's because we said it was to the second power when the function was in factored form. Now, because of the multiplicities, we can tell what does the graph do at those zeros. So odd multiplicities, it crosses the axis. So I'm going to say crosses, right? Because these are both 1 or odd. If it's even, such as multiplicity 2, then it touches. Okay. So I'm going to hop over to Desmos and I'm going to show us what that looks like really quick, just to prove that we indeed did find the correct zeros and that the graph obeys what we said. All right, so I went ahead and graphed the function that we had in Desmos. You can see we do indeed cross the x-axis, or we touch the x-axis, we should say, at negative 4, at 0, and at x equal 1. You'll also notice that we had multiplicity 1 for 0 and for -4. And at those points, it crosses the axis. And the x minus 1 was to the second power, or multiplicity 2. That root was x equal 1. And you'll notice that we touch and turn at that root. All right, so here's another example. We can look at this function and we can say that our degree is 3 and our leading coefficient is positive and it's 1. These are some things that we've gone over in the previous videos. We want to find the zeros. So to find those, we set this thing equal to 0 and solve for x. Now, how might we go about doing that? Well, here, because it's x cubed, x squared, and x, all three of these have an x in common. So I'm going to factor out an x. That will leave this behind. So I have a factor of x, but then I have a quadratic that I need to still factor. So here, I'm looking for two numbers that multiply to -6 and add to -5. -6 can be found by multiplying -6 and +1. Those two added together give us 5. So our two factors are x minus 6 and x plus 1. So let's write it that way. So now we have 0 equals x times x minus 6, x plus 1. This is the polynomial in factored form. You'll notice that each factor is to the first power. Therefore, they all have multiplicity 1. Let's take each of them and set them to 0 and solve to get our roots. So x equals 0, that's done. X minus 6 equals 0, add 6 to both sides, and you get x equals 6. And then x plus 1 equals 0, subtract 1 from both sides, and you get x equals -1. All right, so we have all of our roots. We had already said that these all have multiplicity 1, so I'll put that here. And if each one of these has multiplicity 1, then that means that we cross the axis at all three. Okay, so I'm just going to say crosses. And I'm just going to draw some arrows. And again, let's jump over to Desmos and take a look. All right, so as you can see, I've already plotted the function here. This is in the factored form, so we can see all of the roots. They are 0, 6, and -1. And you can see we cross the x-axis at -1, 0, and 6. Another example here, we have 2x to the 4th minus 18x squared. Again, we're going to set this equal to 0 and solve for the roots. All right, so both of these have a 2x squared in common. So I will factor that out. That leaves me with x squared minus 9. Okay. X squared minus 9 can be factored, or we could leave it in the current form. I'm going to go ahead and factor it, and then we can also look at it the other way if you like. So x squared minus 9 is two terms. That factors as a conjugate pair. So this becomes x minus 3, x plus 3. So if you don't believe me, multiply that back out and show that you get those two things. Also, we have this that tells us that this is the form of factorization for any two perfect squares subtracted. All right. So now I have three factors. This is 1, this is 1, and this is 1. Realize that x squared is a single factor with multiplicity 2. So set each of these to 0 and solve for x. And this is going to tell me then that, right, if I divide by 2 on both sides, then I have 0 equals x squared. Then I would take the square root. Again, that would technically give me plus and minus. I get x equals 0, and this time it is multiplicity 2. Okay. Here I have x minus 3 equals 0. You just add 3 to both sides, and you get x equals 3. Here I have x plus 3 equals 0. You subtract 3 from both sides. You get x equals negative 3. These have multiplicity 1. Okay. So again, it will cross the axis at these points, and it will touch and turn at this root. So we'll go over to Desmos. The function is 2x squared times, let's do x minus 3, x plus 3. Okay. So you'll notice at negative 3 and 3, we go across the axis, and at 0, which is one that had multiplicity 2, we touch and turn. All right, so just real quick, let's hop back over to our form here. The other thing I wanted to show you was if right away you didn't get x squared minus 9, right, you could have solved that by just setting it equal to 0. That gives you x squared equals 9. Then you would take the square root of both sides, remembering that that gives you plus and minus. So you get x equals plus and minus 3. So you still get the 2 roots. It's just a different way of looking at it. It's probably best to get it in this form because this allows you to tell multiplicity, right? The power there tells you multiplicity 2 because these are both to the first power. These are multiplicity 1. All right, last example here for talking about the multiplicity and what that does to our graph. This is already in descending order. The degree is 6, leading coefficient's positive. So we know some things about the graph because of that. If we want the roots, we set it equal to 0 and solve. Notice that all 3 terms have at least an x to the 4th in them. So I'm going to factor that. That leaves me with the following. So I end up with a quadratic here, right? A polynomial with degree 2 that I can factor. So I'm looking for 2 numbers that multiply to 1 and add to negative 2. So those 2 factors are indeed x minus 1 and x minus 1. Now, I wouldn't leave it this way. And in algebra, we typically teach you to do this. If you have x minus 1 times x minus 1, you write that as x minus 1 squared. Now, why did we do that? Well, again, we can very easily get multiplicities, right? These are 2 factors. The first one has multiplicity 4. The second has multiplicity 2. So we set each of them equal to 0 and solve. Right, to get rid of the 4th power, we would take the 4th root, and you get 0, and that's multiplicity 4. Then we have x minus 1 squared. We set that equal to 0 and solve. We would take the square root of both sides. That would cancel on this side, and we'd get down to this. Then we would add 1 to both sides, and we get x equals 1, and this has multiplicity 2. Now, these are both even multiplicities, which means at both of these points, we are going to touch and turn. X to the 4th times the quantity x minus 1 squared. Okay, so it's not as easy to see. We have to zoom in a little. Remember, our 2 roots were x equals 0 and x equals 1. So you'll see we touch at 0 here and at 1, and we touch and turn. This is not a root here. This does not touch the axis. All right. Another thing of note here, notice this is not symmetric. It's shifted slightly from what we saw in the earlier examples. This is because of that x to the 5th term. So if you remember the original equation, right, let's jump back. The original equation was 6th, 5th, 4th. If it was 6 and 4th, it would be symmetric. Because of that 5th term, we are no longer symmetric.